Welcome to section 711. This is the last section of our chapter that we'll be studying here in Math 300 as we get ready for an exam on probability. And so it's another element of probability. This one is an application. And so expected values are exactly that. What we would expect to happen if the same thing was to happen over and over and over again. So for example, from an insurance company's perspective, we want to make sure that we don't overcharge for an insurance policy, or we might price ourselves out of your business, but we certainly don't want to undercharge for it. So we need to know if I charge like $100 for a policy for, let's say, 25-year-old males that don't smoke, and if I charge them that, what's the expected value for a certain payout? And we can look and see, okay, we know at times most of the individuals are going to live through the next year and I'm not going to have to pay out, but occasionally some will. And so I need to know, am I collecting enough money to pay out at those times that the insurance is needed, right? Somebody unfortunately passes away and their family gets the insurance money. And so we need to make sure as an insurance company that we collect enough money. And expected value is one way to do that. And so I mentioned something in there that was important. It really depends upon the likelihood of a 25-year-old male who doesn't smoke passing away. Likelihood is probability. So expected values take into account probability. Here's the way we find expected value. So expected value is a calculation. And I'm going to put it in the terms of the book. It is the sum of all the specific outcomes times their probability. Okay, so you may not have been exposed to this symbol right here. I just want to expose it to you because it's going to be in the textbook if you were to read through it. This just means to sum or to add up, right? Both saying the same thing. So I'm going to use the abbreviations EV for expected value. And so expected value is this. Take every possible outcome and multiply it by the outcome's specific probability. So take every possible outcome there is and multiply them by the outcomes of them happening and add up those results. Okay, that's what this is trying to get you to see. We have to be somewhat formulaic about it, but this is what's happening. So let's have an example to help this definition make sense. So I have the definition right up here. So we're going to take every possible outcome. So here's what I'd like to do. I'd like to roll a 4-sided die that has the standard numbers, that has a 1, 2, 3, 4 on it. So if I'm explaining this process correctly, the first thing that you're going to do is you're going to list every possible outcome. So when I roll this die, a 1 could come up, a 2 could come up, a 3 could come up, or a 4 could come up. Then what you do, and it's always recommended, I recommend it as well, to put it in a table format to organize the numbers that you're going to have to deal with. We need to take the probability of that outcome. So the probability of rolling a 1, well, it's just a 4-sided die. 1's on one side of that. So I have a 1 out of 4 chance to get a 1. I have a 1 out of 4 chance to get a 2, right? So if I focus just on the 2 for just a minute, and I come in here, I'm going to highlight the 2. That's one option out of 4 things that could come up. So that's why it's the 1/4 in there. It's going to be 1/4 for each one of these ones. So 1/4, 1/4. So we're going to take every possible outcome and then multiply each outcome by the specific probability it has. So the next stage Let me make that column a little bit wider. The next stage is to take the outcome times its probability. So the outcome of 1 had a probability of 1/4. 1 times 1/4 is 1/4. 2 times 1/4 is the next one, so that's 2/4. Remember, it just hit the top numbers. 3 times 1/4 is 3/4. And 4 times 1/4 is 4/4. You could have these as the 0.25s, 1/2, 0.75, and 1. I like to leave it in the fraction so that we can trace it back. But now we've done, so here's what we did if I kind of highlight some things. Let me get a good highlighter. Take every possible outcome. Here's what we listed, all the outcomes. Multiply it by each of their probabilities. So we want to multiply those outcomes by each of their probabilities. That's this right here, right? This intermediate one that I'm not highlighting, the probability, is just so we can organize our thoughts. But the 1/4, 2/4, 3/4, 4/4 is the results of the multiplying an outcome times its probability. And then there's one last thing to do, and I'll highlight it in blue, and add up all the results. Okay, so I look at the results that I have, and I had a 1/4 plus a 2/4, I had a 3/4, and I had a 4/4. So the process says just add them up. So I get, if I go from left to right, 3, 6, 10, I get 10/4. 10/4 could be written as 5/2, and 5/2 is 2.5. That's the answer. The expected value is 2.5. And we'll talk about interpretations of this as we go on. Right now, we just want to make sure that the process is okay. So again, to highlight the process, we list all the outcomes. We list all the associated probabilities. We multiply those two things for each of the outcomes, and then we add them all up. So here's an example that's in the book. Find the expected value of a number showing when you roll a special 6-sided die with faces 1, 1, 2, 3, 5, 8, right? So not your standard die. What will happen here? Okay, so as we go to do this thing, let's do it. We know what to do. The process says list all the outcomes. Well, the outcomes that could happen are 1 could show up, a 2 could show up, a 3 could show up, a 5 could show up, or an 8 could show up. Now, I'm not listing that 1 that's on two sides twice. You'll see me account for it. The probability of getting a specific outcome. So as far as what the die can show, the die can show a 1, a 2, a 3, a 5, or an 8. The probability that a 1 shows up, remember it's a 6-sided die, that is 2 times out of those 6. I could get a 1. The 2 only appears 1 time out of the 6, the 3 1 time out of the 6, the 5 1 time out of the 6, and the 8 1 time out of the 6. Again, where am I getting this information? Right up here, they tell me that the faces in these parentheses right here, it's not allowing me to highlight that here. Now it is. That's where I knew the outcomes. And I see 2 1s out of the 6. That's where the 2 6 comes from, right? Just reinforcing those things. So we know that, okay, I take all the outcomes, I find their probabilities using my stuff from earlier, and then I multiply those two things together. So again, when I do 1 times 2, 6, I'm looking at 1 over 1 times 2 over 6, and so I just get a 2 over 6. When I do, let me keep this as clean as I can. When I do the next one, I didn't show these calculations before, but I feel like I can capture somebody that may be struggling. I need to take 2 times its probability 1/6. Remember, fraction multiplication, it's easy. If you have a whole number, it's over 1. So it's 2 times 1 is 2. 1 times 6 is 6. And I get a 2, 6. And for the similar reason, I get a 3, 6, a 5, 6, and an 8, 6 coming through there. Now I got to add all those up, right? That's my last stage, and then I'm done. I'm going to reduce my answer, put it as a decimal from time to time, right? I did on the last one just so you see different ways. So if I add it up, I get 4, 6, 7, 6, 15, 6, 26 is how I'm looking at that. So if you add up all those, you add the top numbers all have to be 20. The only reason we can add them is because they have a common denominator. So I get 26. What would that reduce down to be? 10 thirds. What would that be? 3 1/3. Or my calculator would say 3.33 repeating. Or 3.3 repeating. So however you want to do that, I'll just do 3.33. So 3.33 would be the average in there, or the expected value. So maybe I should be putting that EV equals, right? Adding up all of those. And this was the expected value equals in that regard. Awesome. So then they get some ones that, apologize for all the chicken scratch down here. Then they get some ones that are more complicated. They make you see the space. Find the expected value of the number of heads showing if you flip a coin 3 times. So let's talk about that. As you flip a coin 3 times, we want to know the number of heads showing, right? So we flip it once, flip it twice, flip it a third time. Number of heads that showed up. Well, what's the lowest number of heads I could see? I could see none of them. None of them being heads. I could get tails, tails, tails. But I could get 1 to be a head, 2 to be a head, or all 3 to be heads, all 3 of the flips. The question then is, what's the probability? And the only way to answer this question is using your old skills, right? The skills that you developed in 7.5, but honestly, it's really 7.4 that helps you out. So if you remember, I don't know what the probability of no heads is. I don't know the number of outcomes. Well, great. You don't have to. You just have to be able to say, I know how to determine the sample space. And so you could say, hey, here on flip 1, I could get a heads or tails. On flip 2, I could get a heads or a tails from each one of these. And in flip 3, I could get a heads, a tails, and each one of them. And then you have to see that sample space. That's why we made you write it out. So all of this is for us to be able to answer the probability. That's why they wanted to make sure we had skills of building tables or drawing these tree diagrams. Because what can be seen there, and I'll try to highlight it as I go along, do it in yellow, I see a head, head, head. And so I'm going to write that down. Heads, heads, heads. I also see a heads, heads, tail. Would be a methodical way to list it out, all in that yellow stripe. So let me get rid of that yellow stripe and realize, well, I could be along this path. And what do I see there? I see a heads followed by a tails followed by a heads. And I see a heads followed by a tails followed by a tails. All in that yellow strip. There's 4 of them. I can get 4 more. If I, again, go down and highlight right here, out of that grouping, I can see that I have a tails, heads, heads. Tails, heads, tails. And then if I look at the unshaded grouping below, tails, tails, heads, and tails, tails, tails. So that is what's helping me figure out my probability. So let me get in here and give us some space to come up and see, well, what do we got? How many of these have, I need to get the probability of no heads. How many of them have absolutely no heads? So this is the only one right here that has absolutely no heads. So that's only 1 time out of 8 combinations. Why are there 8 combinations? 1, 2, 3, 4, 5, 6, 7, 8. Out of all those 8 unique outcomes, only this one, number 8, has no heads. So this one is gone, right? We've counted that one. Now it wants 1 head. So I'm going to go in and I'm going to circle all my 1 heads. Here's 1 head. Here's 1 head. That has 2. Here's 1 head. 2, 2, 3. So it looks like I got 3 out of the 8, just having one head. Okay. Let me do the pixel object eraser here, get rid of some objects. Okay. And then I want 2 heads. No problem. I'll come in here and in green, I'll find out where I have 2 heads, and exactly 2 heads. Here's 2, here's 2, and here's 2. Everyone else either has 1 or none. Well, that's another 3 out of the 8. And how many have all 3 of them being heads? Just this one right here. So I'll put that one in black so it's a different color. Just this guy right here. And so that's 1 out of 8. So you're going to have to figure out some probabilities. It's not going to all be just flat out handed to you. And the way we do that, if we don't know what they are, you're normal. That's a normal experience. What we do is we go figure it out. We don't complain. We just go figure it out because we have those skills, right? Awesome. So now you know expected value is taking the outcome times its probability. So 0 times 1/8 is 0. 1 times 3/8 is the same 3/8. 2 times 3/8, let's make sure we look at this. 2 times 3/8 is 2 times 3 over 1 times 8, which is 6/8. And then we have 3 times 1/8, and that is, again, 3/8 coming in there. So now we know what to do. We say, oh, I know how to get expected value. Expected value is simply the outcome times its associated probability, which is our last column, all added up. So 0 plus 3/8 plus 6/8 plus 3/8. So what do we get there? Well, we get obviously 12/8. Again, that bottom number stays the same because that's how we add fractions. You're welcome just to plug it into your calculator. You'll see at times that that's what we have to do. Well, 12/8 could also be rewritten if I divide by 2 as 6. Actually, divide by 4, and I would get 3 halves. I was going to put 6/4, but then it can come down to 3 halves. Well, 3 halves is a perfectly fine answer, and so is 1.5, and so is 1.5. They're all great answers. But the expected value is 1.5. So this next part that they ask about in the homework and that they have as you read through it is interpreting those expected values. The interpretation of expected values is this. Expected values give us the average. It gives us the average if we were to repeat the exercise over and over. Right? Again, Jensen language, they'll say it's slightly different as you read through the book. But here's what's happening. When we get the answer of 1.5, what it's saying is, you're going to flip the coin 3 times, and sometimes you're going to see 3 heads, sometimes you're going to see 2 heads, sometimes you're going to see 1, and sometimes you're not going to see any heads. It's just going to be 3 straight tails. Well, if you did that over and over and over again, and wrote down every time, hey, I got 3 heads, I got 2 this time, I got 2 again, I got 1, I got 1, I got 1, I got 0, and you wrote them all down, and you average those outcomes, they would average to be 1.5. Now, not surprisingly, there's some balance in this weighting. Look at these probabilities. Look where 1.5 is. 1.5 is right in the middle of all the outcomes. There's 2 this way, 2 above it, and 2 below it. And so 1.5 sits right in the middle. It's perfectly centered. The average is what's right in the center. So when I tell you, hey, the average on the test was this, it's saying, well, that scores were above it, scores were below it, and it's right in the middle. You can see here as well. Where's 2.5? 2.5 is right in the middle. So when we roll this 4-sided die, sometimes it's going to come up as 1, 2, 3, and 4. Because they're perfectly balanced, the average is going to be right in the middle. So expected values are the average. That's what they should be writing in the back of the book. That if I were to roll this die, this 4-sided die over and over and over again, average the results, the average would be 2.5. Now notice right here, we got 3.33. 3.33 isn't really right in the middle of all the outcomes. Do you see why that's going to be the case? 3 would have been right in the middle, but there's a couple of reasons why. One reason why, and let me go to a highlighter, one reason why is that we have more weight here that's not balanced. We don't have another 2 6 at the bottom. Down here we had balance, 1 8, 3 8, 3 8, 1 8, so it ends up in the middle. The other way we don't have balance is 1 2 3, and so move up 1 as you go from 1 to 2 to 3, then move up 2, then move up 3, right? So we don't have balance in the outcomes. They're not like in succession like they are here, 0 1 2 3. So it takes into account what I would like to term the weights, both the weights of the outcome as well as the weights of the probability. So for example, with my life insurance example that I talked about earlier, what I cannot change is the probability that a 25-year-old male who doesn't smoke lives through the next year, which will be extremely high. It'll be like 0.999974 or something like that. Very high likelihood that a 25-year-old male who doesn't smoke will be around next year. I can't change whatever that is. So what am I changing in order to get the expected value that I want, which is trying to be profitable but not too profitable when I decide what the policy value is? I use the expected value. I can change the weights of how much I'm charging for the policy, and how much I'm paying out could be the other one I change as well. So it's interpreting expected values. We just want you to realize that it gives you the average, the mean, the center value if we were to do that exercise over and over. There's a couple examples in the homework that are asked about that I want you to be able to understand the setup. And so here's the first one. They talk about this game that's in The Price is Right called Punch a Bunch. So in this game, I'm reading up top here. In this game, contestants have a chance to punch up paper circles on a board. Punch through up to 4 paper circles on a board. Behind each circle is a card with the dollar amount on it. There are 50 of these circles. The dollar amounts are given in this table. Contestants are shown their selected dollar amounts one at a time in the order selected. After each is revealed, the contestant is given the option of taking that amount of money or throwing it away in favor of the next amount. Anita is playing Punch a Bunch and gets 2 punches. If Anita got $1,000 on her first punch, what is the expected value of her second punch? Okay, awesome. Let's make sure that we understand what's happening. So you have this board, and you can picture it as a board with, let me draw down here, won't let me draw up there, with a bunch of, get this back to a pen, with a bunch of circles, right? So these holes, and there's 50 of the holes, and you punch through a hole, and you pull out a card, and the card has a dollar amount on it. So let's say $100 was what was on this card. If you're not happy with the $100, which you absolutely should punch again because you're at least going to get the same, you can punch again. And let's suppose we punch this one and we get on that card 10,000, then we win $10,000. If I get a third punch, I'm risking that $10,000, which obviously you probably wouldn't because of just having one of those represented by the 25,000. So it's got these circles that you can punch, and inside you pull out a card. So here's the breakdown. Apologize. In the table that's above, that's right at the top here, there's the breakdown. There's only one $25,000 card. 2 of the holes have 10,000, 4 of them have 5,000, so forth and so on, all the way down. If we add up all those frequencies, they would add up to be the 50 that are there. So our question is very specific. Anita did her initial punch, and on her first punch, it's telling us that she got $1,000. And so she's debating, do I punch again? Well, one of the ways that she can make an informed decision and not just have it be by chance, right, is to talk about, well, what's the expected value? What's the average because of what's there? And so obviously there's risk involved no matter what. We're just wanting to know, is it worth it? Statistically, is it worth it? So Statistically, it's not worth it for for a 25-year-old male to buy life insurance because their likelihood of them living is extremely high. Is it worth it? Maybe, because an accident could happen, and maybe that 25-year-old male has a child, a wife, and they want to make sure that they're well taken care of in case they pass away. They should be able to get an extremely high amount of life insurance. So if something were to happen, so is it worth it? Yes, right? Depending upon your perspective and your life situation. And same thing here. There's always a risk. The question is the risk worth taking? So let's take a look. So Anita had her first punch and she pulled out $1,000. What's the expected value of her second punch? Well, we just have to do the table, right? And so one thing to remember is that she had her first punch, and I'm going to come up here. Hopefully you can see where my cursor is. It's right here at 1,000. There's no longer 10 $1,000 out there. There are now only 9. And we run the numbers with this. So 25,000 is on the board still. And how many times does it appear? 1 time out of 49. So here's the outcome and its associated probability. Hopefully I explained well why the number is not 50. It's not 50 because we lost one of the 1,000s, right? One of these 1,000s is gone. And that's why I changed the number to 9, and now the total is only 49. In terms of the 10,000, there is now 2 out of the 49. And in terms of the 5,000, there are 4 out of 49. And in terms of 25,000, or 2,500, apologize, we already did the 25,000, 8 out of 49. 1,000, get this down, 1,000, we now know there's 9 out of 49. 500, okay, we know our bottom number is 49. What's the top number for the 500? It's 10 out of 49. 250 was also a 10 out of 49. And I believe 100 was less than that. Oh yeah, we can still see it up there. 5 out of 49. There's my outcomes, the dollar amounts that I could get times their associated probabilities. And so now we know what to do. We do our x times our p of x. Now that's going to be awful if I did it the same way. So I would encourage you not to do it that way. I would encourage you to use your calculator when the numbers are this big. So how do I plug this into my calculator? This is how I would recommend. I'd grab my calculator, type in 25,000 times its probability, which is 1 divided by 49. Hopefully you know that a fraction is just another way to write division. Then you would type in plus and 10,000 times 2 divided by 49. Plus, and what you're doing here is you're adding up all the outcomes with their multiplied by their associated probability. Plus 5,000. Let me make that look a little bit better. I apologize. Went a little crazy there. Times 5,000 times 4 divided by 49 plus 2,500 times 8 divided by 49. And I'm not hitting equals anywhere along the way. I'm just going to let it go into my calculator. Plus 1,000 times 9 divided by 49. Again, it's 9 because on our first one, on our first punch, we removed one of those 1,000s. Plus 500 times 10 divided by 49. Plus 250 times 10 divided by 49. Plus 100 times 5 divided by 49. I'm typing all that into my calculator and I hit equals. And when I hit equals, it will tell me the expected value. So the expected value for our problem, I did this before I did the video, for me came out to be, on my calculator, was 2081.63, and it kept going, but it would round nice to $2,081.63. That's the average of the dollar amounts that are left. That's what I should expect on average. So then the question is, if Anita did get $1,000 on her first punch, should she throw out her $1,000 and take the results of her second punch? How do you know? So you have some instincts here. What do you think? Based on the expected value, should she punch again? Okay. And the answer is yes, she should punch again. And here's the reason why. Because the expected value is more than what she has, is more than the $1,000 that she currently has. So she should risk it because she has a strong likelihood that she will receive more. Okay, and so yes, she should punch again based upon the expected value. If that expected value was under the amount that she had on her first punch, you would not punch again. Okay, so you'll have a question like that. I just want you to be well prepared. You'll also have a question that is involving the game of roulette, which they've done before in previous sections. So here's the scenario. If a player bets $5 on the outcome being odd, the player wins $5. If the outcome is not odd, they lose $5. What is the expected value of their bet, and interpret their results? So there's something very similar in your homework. I think in your homework you're betting on a single number as opposed to even and odd. And there's a second one, but I don't think it's even and odd. So I'm trying to make up something that's similar but different. So let's talk about outcomes. The outcome when that wheel is spun and the ball comes in can be from a verbal point of view, it could be odd, what we're looking for, or not odd. Now, I would highly suggest that you not write even, and I'll show you why, but ideally you already have experience. Language like odd, not odd, even is not helpful in expected value because expected value is a calculation. Okay, so we need to talk about the outcomes, and maybe we should qualify these outcomes a little bit better. So I'm going to qualify the outcomes as win, because the outcome is odd, or lose because the outcome is not odd. When you win, there's a certain money amount that you win. So the dollar amount that you win, according to what's written, is $5. If you lose, you're going to lose $5. But right now, from a mathematics point of view, both of those are wins because both of those are positive fives. So whenever you lose, let me do two things. Whenever you lose and you're out money, you need to put in a negative sign on that loss. A 5 written all alone is a positive 5, which means that from a math perspective or point of view, you get $5. I need to let the math know that if it's not odd, I'm out $5. So just to stress it, I have the negative 5 there. So hopefully you see that there, and I'm stressing it enough. You really need to see a problem like this, because whenever they do betting problems, it's going to be like this. Well, now I need the probability that I win or that I lose. Do you know the probability that you're going to win? Well, sure we would. It would be, if we're going to win, we got to get an odd number, so it would be the number of odds, the number of odd numbers, over the total number of numbers. Do you know what that is? Well, let's look. So here's a roulette table, the same one that they have printed out for you in the book. There are 36 numbers from 1 to 36, but there's also up here, I don't think it will allow me to highlight it, there's also this 0 and 00 right at the top there that we cannot overlook. So there's actually 38 slots that the ball can fall into, and only half of the 36, or 18, are odd. So 18 of them are odd, right? So we have 1, 3, 5, 7, 9, 11. If I add all those ones, I'm going to get 18 that are odd. And how many are not odd? Well, 18 between 1 and 36, but also 19 and 20, way up here. Don't forget to count those too. So what did I learn, or what can I see? And you can back up the video if you want to see it. But there are, sometimes it's like this. There are 18 numbers. Not sure why it's immediately erasing. I think it had a glitch type of thing when I did this before, when I went to the roulette wheel. So let me close that down, see if that helps. Okay. That's going to be annoying. Let's see if it works up here. Okay. Let me just go in here, erase here, and see if I've created a problem there by going back and forth. Okay, cool. So we're just going to come up here. So I'm going to translate some information. What we decided is if we're going to win, we win $5. If we're going to lose, by not getting odd, we're out $5. And so that negative sign is really important. The probability is what we were just after, and I wanted you to see it. What we saw was that there were 18 out of the 38 slots that were odd, and 20 out of the 38 slots were not odd. I can't say that they're even because the 0 and double 0 are neither even or odd. So there's 20 numbers where I could absolutely lose. So now we have to do our x times our p of x. So what would I recommend? I'd recommend not finding them out individually. I would recommend using your calculator and typing in 5 times 18 divided by 38 plus negative 5 times 20 divided by 38. And I would hit equals. When you hit equals, you're going to have negative 0.26, and it's just going to keep going. We're dealing with dollars, so negative 0.26 is the expected value. Well, let's talk about what that means, right? Because the question was interpret your results, right? The question's down here at the bottom. So this is the right answer, negative 0.26. So what does it mean? It means that the player is losing money, because this was all from the player's perspective. If we win $5. If we lose $5. So it's showing you that betting on odd is not a game that you will end up winning at. If you did it over and over and over again, you would lose 26 cents every time you bet $5. Okay, it doesn't sound like a lot, but let's suppose I played that game 1,000 times in a row, hoping to win. What it's telling me is my expected value would be 1,000 times 0.26, but negative. It shows me I'd be out $260. I would have had put all that money in, but because I'm going to win some and lose some, I'm going to lose more often. That's what this is showing. You're going to lose more often. And on average, it's going to be about a 26 cents loss every time I place that bet. Sometimes I won't see that, and sometimes I won't see that for a long time. But if I play a large amount of times, like 1,000, it should even out. And even out to be about 26 cents per time. I'd be out $260. I'd be down $260 if I had played 1,000 times, is what I should expect to happen. So it's showing you that the casino is making money, right? And so the casino looks at this and says, this is awesome. I'm keeping it to be a kind of low profit gain relatively from the player's perspective. So they're going to come and play because they really feel like it's a 50-50 thing, even though it's not. And I'm going to collect 26 cents from them every time they're playing on average. So there's times I'm paying out as a casino, but there's more times that I'm collecting money in and just keeping that $5, right? There's a lot of people that go in and out of a casino. So over the course of a year, let's suppose that there were 2 million people that place bets like that. And I don't think that's an uncanny number. Well, those 2 million bets would have resulted in, let me just see, 0.26 times 2. A net gain for us of over $500,000. $520,000 just on people placing those bets, right? And you know that there's strong numbers for other bets that are being placed all throughout the casino. But What's the results? What's the interpretation? Oh, shoot, it's a loss for the player. Probably shouldn't play this game. Hey, on average, even though the casino is going to take in $5 and pay out $5, and the rate's the same almost, but it's slighted towards the negative. Hey, the casino is going to make money on this, and on average, 26 cents for every $5 bet is what they're going to make. And we can make a lot of money just taking a little bit every single time. So that's the idea of expected value. I wanted you to have some examples that were in the book and also just lay the foundation. So hopefully you feel that that's a good foundation for